Welcome to our presentation of a study of the effects of sewage contamination in the Ala Wai Canal, a study of metal contamination by location. I am Courtney Kubata, and along with Rachel Key, William McQuiston, Michael Mount, and Kevin Suzuki, we represent Iolani School from Honolulu, Hawaii, United States. We hope you enjoy our presentation.
The Ala Wai, we will start off with a brief summary of the Ala Wai Canal, which is located near Waikiki. Then we will explain and analyze the data taken directly from the Ala Wai and give our conclusion. To start off, we chose to analyze the Ala Wai Canal because of its importance and proximity to both Waikiki and our school. The canal serves as a major tourist attraction and is a well-known site on Oahu. The Ala Wai is used to divert rainwater from the mountains. Also, it is a habitat to many aquatic species. Our school uses the Ala Wai Canal for its paddling and and kayaking competitions.
Though Waikiki is known today for its hotels, resort areas, and beautiful beaches, it was once a wet swampland composed of many rice paddies. The Ala Wai was thus built in 1928 to drain the swampland of Waikiki. After its creation, the canal had to be frequently dredged in order to prevent overflowing. In 2006, after heavy rainfall, a main sewage pipe broke, and for 3 days, sewage spilled into the Ala Wai. So thus, our purpose is to analyze the dredging of the Ala Wai Canal and the effects of the sewage spill. The majority of our analysis will be based on the metal concentrations and bacteria level of specific locations of the Ala Wai.
The Ala Wai is a habitat to several organisms, including tilapia, jellyfish, crabs, shrimps, copepods, and bacteria. These are some of the few species that can exist in the harsh conditions of the Ala Wai Canal. There is also a variety of pathogens that exist in the Ala Wai. Some of these include colonies of Vibrio, Salmonella, Shigella, rotavirus, adenovirus, enterovirus, Norwalk virus, and pathogenic E. coli. These pathogens cause the water quality of the Ala Wai to be deteriorated.
The Ala Wai receives its water from 3 streams, the Manoa, Makiki, and Palolo streams. The Manoa and Palolo streams add the vast majority of the water to the Ala Wai through the Manoa and Palolo drainage canal near the beginning of the canal, and the Makiki stream supplies a small portion of the water near the beginning of the canal. During storms, water is also supplied to the Ala Wai through several storm drains along the edge of the canal.
The Ala Wai Canal is an estuary exhibiting a saltwater structure in which lower salinity and lower density freshwater from the streams flows over a layer of higher density and higher salinity saltwater, which thins as one moves upstream. The Ala Wai Canal also exhibits tidal flushing, in which the wedge of high-density saltwater is carried into the upper reaches of the canal during high tide. The Ala Wai Canal flows far slower than the Manoa and Palolo drainage canal, which flows into it. As such, the sediments from the erosion of the Ko'olau Mountains, which are suspended within the higher flow of the Manoa and Palolo streams and drainage canal, settle out in the water column when they encounter the slower-moving Ala Wai water, forming a cell of sediment that needs to be periodically dredged to prevent flooding. This dredging removes over 165,000 tons of sediment and mud from the Ala Wai Canal and destroys the historical sediment record of the center of the canal. In part because of the destruction of the historical record, there has been no study of the metallurgical content of the Ala Wai Canal since 1995, when Eric DeCarlo and Cleo Spencer took 4 core samples along the Ala Wai. They found elevated concentrations of copper, lead, and zinc, which they believed to be human caused. Furthermore, they found that while zinc and copper were increasing in concentration up to the point of their research, lead concentrations had begun decreasing from a maximum at around 1975 with the passage of legislation banning lead additives in gasoline.
The 2 main inputs of contaminants are the sewage spill of 2006 and the storm drains located along the Ala Wai. The sewage spill originated at this point in the Ala Wai. The storm drains, located along the Waikiki side of the Ala Wai, also emptied a large portion of contaminants. The sewage spill led to many negative effects. Initially, bacteria and viruses were released into the water. Overall, these effects were catastrophic, resulting in the temporary closure of Waikiki beaches. Since the spill, there has been an increase in the level of bacteria, causing a wretched odor, unsanitary water quality, and the destruction of aquatic habitats.
As we stated, the contaminants from the sewage spills even into the aquatic life that lives in the Ala Wai. An example of this is the discovery of a 38-centimeter mantis shrimp weighing 0.6 kilograms. There were also various cases of uninformed tourists who caught a few tilapia and ate them. These tourists were ignorant of the high viral concentrations in the fish. Thus, some of them became sick. The consumption of the fish is not the only source of sickness and disease connected to the Ala Wai. Oliver Johnson, a local Hawaiian, contracted a viral infection and later died due to his infections of cuts and wounds he accumulated prior to falling in the Ala Wai. However, many statistics show that a typical healthy human being would not have died under the same circumstances. Even though some of our kayakers fall in the Ala Wai, the majority of them do not become sick nor contract infections. Therefore, we conclude it is not advised to come into contact with the Ala Wai water or wildlife pertaining to the Ala Wai, but even if you do, it should not have too big an effect on your health.
For our experiment, we divided the Ala Wai into 14 different sections, some of which include the main parts of the stream and the Manoa estuary. This allowed us to compare the metal concentrations in the different parts of the Ala Wai and look for trends in the buildup of sediments. Mr. Evan Roberts, one of the staff at Iolani, kindly took us in his boat to collect the mud and water samples. We caught one average-sized tilapia and several smaller fish. We took mud samples from the bottom of the canal using a mud clamp that we borrowed from our school's AP biology lab. The mud clamp is designed such that the box snaps close when coming into contact with the bottom of the canal. They also gave us advice pertaining to the collection of data and recommended us to take samples from the center of the canal. Water samples were taken from the top layer of the canal using sterile containers. We dissected the tilapia in our school's biology lab. We separated the fish entrails from the flesh and tested them for metal concentration in each part. For the smaller fish, we dissected the collection as a whole and stored them in a plastic container.
We took the fish remains, water, and mud samples to the University of Hawaii for a metal analysis. Professor Raymond Nishida and Professor Robert Huang from the Agricultural Diagnostic Service Center allowed us to use his laboratory for the metal analysis. He explained to us what equipment to use and how each device worked. We used a spectrometer to analyze the metal content. The metal sample is put into the source and a high-energy beam is shot through it, exciting the electrons in the sample and turning the sample into a glowing plasma. The plasma emits light, which is then reflected by mirrors and into a diffraction grating. The light is separated by the grating and is then fed to a computer for quantitative analysis. Different metals will emit different wavelengths of light at different angles, thus allowing us to determine the concentration of different metals in each sample.
This is our raw data of metal concentration in the mud, fish, and water. As you can see, the metal concentrations in the water remain fairly constant throughout all the sites. However, the concentration in the mud shows some anomalies. We based the majority of our analysis on these anomalies. The metal concentrations in the fish also show that metals enter the various organisms of the Ala Wai. We compared our data samples from the Ala Wai with that of Lake Biwa Canal and tap water in Hawaii. We wanted to compare the metal concentrations of the Ala Wai to relatable sources in Japan. In comparison to Lake Biwa and Hawaii tap water, this graph indicates that the metal concentration in the Ala Wai is similar to both waters because they all have a concentration that's very near to zero. As shown in this chart, the metal concentration is fairly similar, and thus we find that it was not greatly affected by the sewage spill.
We graphed our results by site and concentration with boxes to represent the concentrations found in the prior 1995 study. We divide our data into 4 graphs, 2 graphs for metals with greater than 1 part per million concentrations, and 2 for those with fewer than 1 part per million concentrations. Then the 2 graphs of each set of metals were divided according to whether the data was taken from the Ala Wai Canal or the Manoa and Palolo Drainage Canal. Where we visit these graphs in the discussion.
Along the residential side of the Ala Wai, there were many small pipes, but there were 2 main storm drains along sites 9 and 10. The storm drains come from Waikiki and hotel area and empty into the Ala Wai. These commercial areas of Waikiki empty a fraction of the metals into the Ala Wai. The sewage spill had a significant effect on the mud. The increase in E. coli concentration in the mud and soil increased its toxicity and also changed its color from brown to a brackish black color. As a result, a foul stench emanates from the mud and the canal. We found that the fish had a higher concentration of metals, especially in their guts. It is thus advised not to catch and eat the fish that inhabit the Ala Wai because of such high metal concentrations. We can see the effects of biological magnification as the fish have a much higher concentration of metals than the water.
The In order to count the bacteria, the prepared water sample is poured evenly into IDEX quantity trays wells and sealed. After 18 to 22 hours, the bacteria is allowed to incubate. We counted the amount of large to small yellow wells and the amount of fluorescent wells using a black light. Yellow wells signify the existence of coliforms, while yellow and fluorescent wells signify the existence of E. coli. The results, or the number of positive results in the small and large wells, is then correlated to a most probable number table to quantify the amount of coliforms in E. coli. The sewage spill deteriorated the water quality by releasing a high concentration of bacteria along the canal. Even though the bacteria concentration increased throughout the Ala Wai, the overall metal concentration was not altered. Regardless, life was still impacted both in and out of the canal.
The concentrations of selenium, arsenic, and cadmium were at very low levels and were essentially constant with their concentrations upstream in the very beginnings of the Makiki, Manoa, and Palolo streams. Therefore, we have determined that these minerals are derived from natural mineral content and are not caused by anthropogenic activity. Likewise, nickel and chromium are essentially constant with the concentrations measured upstream. However, copper, lead, and zinc were at levels around 100 parts per million, greater than the normal background levels that we found upstream. These metals were especially concentrated at sites 9 and 10, where storm drains channel runoff from Waikiki in the canal. We believe that the copper came from the wear of car brake linings, that the zinc came from the wear of vulcanized tire rubber, and that the lead is coming from runoff of soil previously contaminated by lead additives and gasoline. In conclusion, regarding metal concentrations within the Ala Wai, water concentrations at the top of the water column are essentially clear of toxic metals, and sediments containing the heavy metals remain suspended within the flow of the Manoa and Palolo drainage canal and settle out in the low freight of the Ala Wai. The concentrations of zinc, copper, and lead are primarily human caused, and they are derived from the runoff of the Waikiki area. We believe that the improved durability in the materials has resulted in the decrease in concentrations from the 1995 study, and that the high levels of metals in the concentration are preventing the native species of fish from surviving while giving tilapia an unfair advantage.
As for bacteria, we conclude that the sewage spill led to an increase in bacterial colonies in the Ala Wai. Bacteria is also evenly dispersed throughout the canal, and the unsanitary water quality of the canal originated in the high levels of bacteria.
As for further research projects, we can try to keep sampling the sediments in the canal where it is likely to be dredged. For health concerns, we can try to find past health records of those who worked on the Ala Wai. We can also look into strategies of remediation of elevated concentration in water and sediments.
Although the Ala Wai is contaminated due to the high levels of bacteria in the water, the contaminated water does not spread into any of Hawaii's other water systems like our drinking water. Thus, the water in the canal is very well contained and does not interfere with the natural reservoirs of Hawaii. Therefore, it is very safe to come to Hawaii and drink our naturally purified water. Thank you.